All right. Uh, just going the remaining part of this chapter. Before I go over the remaining part of this chapter, I want to clarify a few things, not to for you to get confused. Um, when we are talking about the charged particle moving in an external magnetic field, in your book, textbook, this says the fingers pointing in the direction of the magnetic field and thumb pointing in the direction of the motion of the charged particle. If it's a positive charged particle, then the line coming from out of the palm, which is going up, which is perpendicular line, is the direction of the force. If you have a negatively charged particle, and then it means the thumb again pointing in the direction of the motion of the charged particle. This is the direction of the external magnetic field, and the force is this way. Alrighty? So this is one thing, F is equal to QVB sine theta. And then we also talk about the magnetic, the current carrying wires. So in the case of the current carrying wires, here I want to also look at this, that in this case scenario, the magnetic field, this is a positively charged particle, so we want to see what is the missing component here. If you look at this, we learn F is equal to Q V times B, right, or this is equal to QVB sine of theta, right? So now here F is there, V is there, B is missing. Now if I use the same thing principle, that the force is coming out of the palm, so velocity of the particle is up there, that means the magnetic field is in, right? So the magnetic field is missing, which will be here, the magnetic field. Okay. Now for this next one, the velocity vector is down, magnetic field is in. So what you're going to do is this, right? So which means the force on that is going to be, this is the velocity vector, this is the magnetic field going inward, so the force is going towards that way. Okay, so which means the force is here, that is the missing component. Now if you look at this part, here the velocity vector is given, and positively charged particle we will use the right hand, so which means my thumb points in the direction of that, the force points upward, which is this, okay, then the magnetic field is inward. Already? Sorry, the magnetic field is going to be like this. Okay, the magnetic field is outward. So for that part, the magnetic field is outward. Force is up, particle is going this way, the magnetic field is here, coming towards you. So the magnetic field is missing here, which is outward. Okay, that is another part. So which is also here, if we look at this, all three things are there. Alrighty. So now, having said that, I want to go quickly to this part. So for this part, I know I mentioned that you can use either way, but if you want to stick with what I talked about, the charged particle moving, positive charged particle, the fingers in the direction of the magnetic field, thumb in the direction of the moving charge, then the line coming out of the palm is the direction of the force. Let's keep the same over here, because if you don't want to get confused, because some of you might get confused. So there are several ways, as I said. So which I talked about someplace in the class, maybe this way is also fine, but let's follow the same way here. Now if the charged particle was moving along the direction of the thumb, Now the current is moving along the direction of the thumb, okay? And then the fingers pointing in the direction of the magnetic field, and the force is coming out of the palm, right? So this is the similar to what you learned about the charge, okay? So here is the direction of the motion of the charge, here is the direction of the current. And then these fingers point in the direction of the magnetic field, and this is the force on the current carrying wire placed in an external magnetic field. Alright, so earlier if I have told you about this, where you have the fingers in the direction of the current and then curl toward the magnetic field and thumb points that, which will be same as this, but you know, if you want to stick with this part, with the the charge moving this way, magnetic field this way, this is the force. Current moving this way, the magnetic field this way, this is the force. Okay, so same thing for the two. All right, so which means I can do this. I can get rid of this if you don't want that, right? So the same thing we apply over here. Then I do this. Okay, so you can apply the same thing over here. Now the current carrying wire, magnetic field into this. Now the direction of the current is here, up going this way along the thumb, and then this is the force. And sure enough, the force is this way. Okay. Now for that, the same thing. The current is here, but the force is going to be this way. Okay, opposite. So this is the force. So here is the force. Got it? You can also do by curling the fingers, but I think let's stick with that. Anyways, now moving next. So I want to talk about a little bit about this Ampere's experiment about the current carrying wires, and then they are placed parallel to each other. So if you look at this, these current carrying wires carrying the current in the same direction. Now what is going to happen is, now this length of the wires is given to you 1 meters, and these two wires are 1 meter apart from each other. Now the magnetic field due to this wire, this is carrying the current here, it is affecting this first wire is here. Okay, that is the magnetic field. This is due to first wire. Okay, let's call this 1, let's call this 2. Okay, so this is B in is the magnetic field due to the first wire. Okay, now here is the magnetic field B out, which is due to the second wire. So if you look at that, the second wire, the current is going this way. The part of the region, the looping around region which is affecting the first wire is the magnetic field coming out. Okay, keep in mind we said if a current carrying wire has a magnetic field around it, and that magnetic field we find out by grasping the wire in our visualizing the grasping the wire in our right hand, thumb in the direction of the current and the magnetic field around it. That is the magnetic field produced by this wire. The same is here. The magnetic field due to this wire is here. Magnetic field due to this wire is here. Okay? Now, that magnetic field, which we talked about it, first of all, I want to say a few things about the force, right? So we talked about the force on a current carrying wire. Then we also learned about the force due to the electric charge, which means due to the electric field, and the charged particle moving in external electric field. So that we said this is the magnetic field lines. So going from positive to the negative, so it will be kicked, right? So it will go like that. Then there is a magnetic force, gravity, we talked about it, and the force due to the current carrying wire placed in an external magnetic field. Okay. Now we talked about the current carrying wire. So how do I know how much is the magnetic field produced by the current carrying wire? So in order to understand that, we said we can do the following, that if I pretend that I am holding the wire in my right hand such a way that thumb points in the direction of the current and the curved fingers looping around the wire will tell you the direction of the magnetic field produced by this current. Okay, so this is shown over here. So this is if you look at the circle 1, circle 2 and circle 3, the magnetic field in the circle 1 will be stronger, in circle 2 will be weaker, and circle 3 will be more weaker. So which means this magnetic field is proportional to the current in the wire. More the current, more the magnetic field. Also the separation, the distance between the distance around the wire where you are looking at it. So more the distance, less the magnetic field you feel. Small the distance, closer to you are to the wire. For example, in circle 1 you will feel more effect of the magnetic field produced by the current. In the circle 2 you will feel less effect because R is larger, B is smaller. On the other hand, current, increase the current, more the magnetic field. So which means this is equal to mu naught, which is the permeability of the space through which the magnetic field moves, divided by 2 pi r. And if you look at this, 2 pi r is the circumference of the circle. So this is how you can find, this is called the Ampere's law. Okay, the Ampere's law tells us how to find a magnetic field due to the current carrying wire. Now this mu naught is the permeability of the free space, and this is a constant. This has the value of 4 pi into 10 to the power minus 7 Tesla times meters over ampere. Okay, so as you see over here, the magnetic field along the circle is a tangent to each point. So as you away from the center of the wire, from the wire, the magnetic field is smaller, larger, larger, larger as you go coming closer to them. Okay. All right. So now, so this will be we learned few things. The magnetic field on the current carrying wire, which is that. Now if I curl this wire, becomes a loop, the magnetic field is going from north to from one end to another end, which will looks like there is a magnet placed inside the loop of the current carrying wire. Okay, now it's a circular wire. Okay, and then if you join several circles, that will make a solenoid. So there is a way to find out depending on the geometry to the magnetic field, but you don't need to worry too much about these two. So here only you need to know how you can magnetic field looks like, but mostly you have to worry about how to calculate the magnetic field over here. Okay, for the straight wire. Now here is a question that it says now you want to find the magnetic force on the current carrying wire. So there are two wires parallel to each other. So one wire is here, the other is here. The current in a wire 1 is in this direction towards right. Current in a wire 2 is also towards right. Now since there is a current, from the Ampere's law there will be a magnetic field. If I take I hold these wires in my hand, the current moving that way. So if I'm looping around my hand around this wire by keeping the thumb towards the direction of the current at the upper wire 1. Okay, so I1. So at the back of the wire, the magnetic field is coming like this. At the front of the wire, the magnetic field is going down, and at the bottom, the magnetic field is going into the page, and that is where the magnetic field due to this wire is B1 over here, which is going into the page. Okay. Now similarly, for the wire 2, the magnetic field is, in this case, the magnetic field at the top is coming towards you, At the bottom, if I circle around, loop around, then at the top it's coming towards you outward, right? At the bottom is here, right? At the top it's coming towards you, right? Outward. So which means that is the part I am interested in, because this is where it's going to affect this first wire. So the magnetic field B1 is here, sorry, B2 is here, okay? Now that B2 is out of the page. Now this is the distance between the wire, which is the radius of the wire at which you are looking at the magnetic field, right? Like this, I current, magnetic field, B is equal to mu naught I, let's say this is called I1 B1, I1 over 2 pi d, right? 2 pi d. Same way here. Now here the external magnetic field, so the magnetic field due to B2 has a value which is due to the current I in the wire I2 is this, right? Whereas I want to find the force on the wire 1. So the force on the wire 1, now this B2 acts like an external magnetic field. So the force on the wire 1 is going to be current in the wire 1 times the length of the wire times the magnetic field B2, which is an external magnetic field, right? So this is going to be I1 times LB2 sine of theta. The theta between the current and the magnetic field is 90 degree. So this is 90 degree. This becomes 1, right? Sine of 90, theta is 90 degree. So the sine of 90 is 1, right? Now let's join, because I don't know the magnetic field B2, but I found out the relation which can tell me the magnetic field B2 due to the current I2, right? So I'm going to replace this B2 over here, okay? Or here, whatever, okay? So which means that will replace the magnetic field B2, right? Over here. So let's do a little bit of math. So F1 is equal to I1 L, instead of B2 I will write mu naught I2 over 2 pi d. Okay, and simplifying it, it says mu naught I1 I2 L over 2 pi d. Now if you look at this, the force, now I can find the force even on 2, which also will be similar if I know the distance, of course, which d. So it only involves the two currents. It does not have a magnetic field inside the, what is the strength of the magnetic field, okay? So that is why, that is the need. So you can only find, you can find the force with this relation. Now here it says force per unit length. So you divide the length on both sides, so you can get the force per unit length, okay? Alrighty, now, so these are the two conducting wires. We talked about this earlier. So, and we can find the force between the them two. So the force over there is due to B2 up there, which is affecting this wire 1, and here is the B1, okay, affecting wire 2. So these forces are attractive forces. So now you can find the force between the two. Now let's go further. I want to talk about here the force per unit length, okay, and then to find the current, okay, between the two current carrying wires, they carrying in the same direction. So what I'm going to do is the following. So the question says two wires each having a weight per unit length, which means weight per unit length is mg over L, which is 1 into 10 power minus 4 Newton over meter, are strung parallel to one another above the surface of the earth, one directly above the other. The wires are aligned north to south, okay, north-south, and when their distance of separation is 0.1 meter, what must be the current in each of the wire in order for the lower wire to levitate with the upper wire. Alright, so you are given the weight of the wire mg over L, which is this, right? So wires are separated between them. Now their separation is same. The magnetic field is basically what it says about the magnetic field. We don't need the magnetic field at all, as you know. So what I'm going to do is the following. We know that we want to find the current, so we know the relation F1 over L or F2 over L is equal to mu naught times the current in 1 times the current in 2 divided by 2 pi d. Now let's say I1 is equal to I2 and this is equal to I. Okay, so I can replace that. This is equal to mg over L. This is equal to mu naught times I square over 2 pi d, and from here I rearrange it, and I square is equal to 2 pi d times mg over L. Okay, mg over L times mu naught. Okay, so that is what is happening over there. So you can find the current from there. So this will be I square, and then you can square root, and that current comes out to there. Okay, so this is what answer is. This is square, you have to take the square root over here. Got it? Okay. Now here is another point. You see, you have a current carrying wire. What is the magnitude and direction of the magnetic field at point P? So you want to find the direction and the magnitude of the current at point P. Okay? So what you're going to do is using Ampere's law. So the magnetic field at this point B is equal to mu naught over 2 pi r. R is this 1 centimeter, which is equal to 0.01 meters. Okay? Now you can plug in the numbers and we get it. The current is 15 amps given to us. So you get the answer 0.3 millitesla. So here are the two wires, which says these two wires carrying a current in the same direction. They are separated by a distance 0.2 meters, and you have to find the magnetic field on either side of the wires 0.15 meter distance. So this magnetic field will be due to this wire and due to this wire. This magnetic field will be due to this wire and due to this wire. Okay. So now if I look at the side view of the wires, it looks like this, because the current is in the same direction away from me. Okay. The magnetic field due to B1, you see here the magnetic field is up, and due to B2 is also magnetic due to coil 2 is up. Now if I look at here, the magnetic field B1 is down due to this, and B2 is also down, right? So I can find only for one of them, then the other one is all set. Now the magnetic field B1 due to the current carrying wire 1, which is equal to mu naught I or 2 pi d, which is 0.2 times, okay, over here. 0.2 is this distance, okay, and this is 0.15 again. So you will have 0.2 plus 0.15. Now the magnetic field B2 due to wire 2 is this, which is 0.5 meters, 15 meters, so you do that. Then you can add, since the two magnetic fields are in the same direction, you can simply add them up. Although they are vectors, be careful. So they are in the same direction, you can add them up. Okay, if they are in the opposite, you have to subtract. So you can add them. So the same should be for the wire 1. Okay? Okay? So whatever the B1 plus B2 total B you find on this side, okay, B1 plus B2, same will be B is equal to B1 plus B2 over here. Okay? Alright. Now coming back to, once we talked about that, I want to remind you about the torque, the idea of the torque, which we discussed in physics 1. The torque is displacement times the force, right? Sine of theta. So basically, in order to rotate the torque, in order to If you want to change the tires, you need to use the torque, right? The rotational force analog to the force, okay? Not a force by itself. Now the angle is the angle between the displacement vector from the point of application of the force to the point of rotation, okay? And the force is applied at the point of application. If the force is perpendicular to the displacement vector, then you get the maximum torque, okay? If the displacement force is not perpendicular, it's some angle, then the torque depends on that. So this has an important implications in here, electricity and magnetism. So what is going to happen is the following, that I will do this. So all right, so this has an important implications in the which we call the electric motors. So what happened in the case of the electric motors, you have two magnets on the sides, and then you have a conducting wire which is in the form of a loop, almost a loop, and then it's rotating between the two magnets, and you provide the electric current to the one end of this current loop through the electric wire loop, and on the other end you can hook up with some machine so that it will rotate, like fan or motors or whatever. This is all in your kitchen, okay? Just start with your kitchen. So this is the electric fan which rotates, all right? Now what is going to happen is, you see the magnetic field lines move from north to south, right? This is the magnetic field lines. Now the current carrying wire, the current goes from positive to the negative terminal. So let's say this is the positive terminal, current goes from here. This is the direction of the current over here, I, and direction of the current over here, I, the direction of the current over here, I, and the direction of the current over here, I. Right? So let's look at this. Now within the magnetic field, so I put that part over here now. So in the kind of whole closed loop. So the current is moving like this, okay? So let's see, if I look at this, so at the end here I put the mechanical part so that it will start rotating. So in the electrical motor, what you do is you provide the electrical energy and you do the useful work with that. That is called the mechanical work. So electrical energy is converted to the mechanical energy. So if I look at this part of the wire, magnetic field is that way, so the current is going this way. So what is the force on that? So the force on this is going to be downward, right? That's what the force is going to be. That's what you see over here on this part. Okay. Then if I come on this part, so the current is going that way, and the magnetic field, basically here the current was going that way, and now in this case the current is coming towards you. This is the thumb pointing the direction of the current, okay, and then magnetic field is this way, okay. So as a result, what is going to happen is the force is going to be upward direction, right, here in this side. So that is what you see, the force is in the upward direction. Now what about the force on this side, two opposite sides? I label them. This is side 1, side 2, side 3, side 4. So 1 and 3 we find out this is the direction of the force. How about 2 and 4? Both sides 2 and 4 are not in the magnets, okay? Even if they are, you cannot find the, so you see if the direction of the current and the direction of the magnetic field is same, so the force is 0 over here, and here the direction of the current and the magnetic field are opposite, the force is 0 over here. So only these two arms, they are rotating, the force is in the opposite direction. So in one way the force is down, the other is force is up, so that is rotating. Okay, so this will be keep rotating, that's how the motor is rotating. Look at, you see that, right? Now, let's say the two arms have the force F, we call them F1 and F2 or F1 and F3, whatever you want to call it. So this is going to be the force, this force is going to be I times the length of the wire, which is here, the length is B times the magnetic field, right? This is also going to be I times the length of the wire, which is B times the magnetic field. Alright? So if we look at this, now as I said, the electrical energy used to do the mechanical work, so it's the rotation part, so the torque comes into play. So the torque depends on the force, right? Torque is equal to R times F, and here the F is, this is the F, okay? This is the F. Got it? This is the F. Okay? Now, the torque is R times F times sine theta. Okay? So, let's see. R, what is R? R is the distance from the point of rotation. The point of rotation is this. So, if this length is A, okay, then this is A by 2. This is also A by 2. So this distance is A by 2. Okay. So the torque due to this force is in one direction, the other direction. So basically the torque is in the force. So the counterclockwise torque. So that is positive. You can add the two torques. So A by 2, R is A by 2 times F plus A by 2 times F. So the total torque is tau 1 plus tau 2, which is equal to A by 2 times F due to 1 plus A by 2 times F due to 3, okay? Where F1 is equal to F3 is equal to F. Alright? So we do that. So basically A by 2 plus F, this I can write A by 2, which is here, A by 2 times F plus A by 2 times F. So this becomes A times F. Alright? Now what is F? So torque is going to be A times F, and F is basically I times the length of the wire times the external magnetic field. So that is what it is. Now A times B, little a times B is the area of the rectangle times the current times the magnetic field. So I can write this is area times the current times the magnetic field. This is a torque. Now if there are n number of turns in the loop, if this is for a single loop, if there are n number of turns in a loop, I can multiply this with n, okay? And keep in mind, we can also write this n area times current times magnetic field. That is torque, right? So this is going to be n area times current times magnetic field sine of theta. That's the torque. Now the reason we need the torque, because in order to do that, we need to know how much mechanical work we can do with the motor, right? So we can find the torque of the motor, right? So torque due to the magnetic field on a wire. So that will give you the torque for the electrical motor. So here is a question that a circular loop of a radius 50 centimeter is oriented at an angle of 30 degree to a magnetic field, then of 0.5 Tesla, the current in the loop is 2 amps, find the magnitude of the torque, okay? So what you do, torque is N times B times I times area times the sine of angle. So sine of the angle is 30 degree, which is given. Now area of the circular loop area of the circle. What is the area of the circle? Area A. This is equal to pi r square. Okay, that's where you need r. Then the magnetic field is given, the current is given, the number of loop is 1, so you can find out the torque, which is 0.39 Newton times meter. Alright, so this is pretty much about this chapter. You just a little bit want to mention about the cosmic rays, that the cosmic rays are electrons, protons and other elementary particles. These are produced by the astrophysical processes, which is include the those processes, including the processes happening in the sun and the source outside our solar system. Now the Earth's magnetic field is served as a shield. We have to be thankful to the Earth's magnetic field against these harmful cosmic rays, causing this Earth's magnetic field deflect those charged particles coming in the cosmic rays. Okay, that is where you see up there, right? So the magnetic field on the particle, if positively charged particle, this get trapped in the magnetic field of the Earth. Okay, and does not harm you like this. But not only this, this also creates a beautiful pattern for us that is called the auroras, right? So the charged particle moving on the Earth's magnetic field flow in a helical path like this around the magnetic field line, and they form these northern lights. They are beautiful lights if you have ever had a chance to look at this. So these auroras look the beautiful light. So basically this natural display. You see from the charge, this electromagnetic radiations coming from the sun in the form of the particle, they got trapped in the Earth's magnetic field, and then they produce the auroras on the northern, on the edges of them, right? You see in the oval part, you see there is a auroras produced over here. This is magnetic shield is saving us from the harmful cosmic rays. Alright, so this is beautiful lights one can see on the northern regions. Okay. Well, alright, so let me summarize that what we did so far. We did here this table, which basically gives you the comparison between the electric and the magnetic fields. So what it tells you, if you look at the first column, which is the source, and the second column talks about the electric field, and the third column talks about the magnetic field. So in the first electric field, the source is a charge. In the magnetic field is a moving charge. Okay. Here the electric field, the charge is just static charge. Here the charge is moving. Now this electric field of course acts on the charges. This also, the magnetic field acts on the moving charges, not the still charge. The electric force is F times QE, and magnetic field is QVB sine of theta. Alright, so then the direction here, the electric field is parallel to the force, electric force, and the magnetic force is always perpendicular to V and B. Alright, so the electric field lines serve as a radial, just like you put the paper pins around the ball. Alright, and then the magnetic field lines are around the moving charge. Alright, so the same charges attract opposite charges, the same charges repel, opposite charges attract. Over here, the currents in the same direction, they will attract, and the currents in the two parallel wires in the opposite direction, they will, the currents in the opposite direction, they will repel. The two wires will repel each other. In the same direction, they will attract each other. Alright, so the next part is the magnetic materials. So there are three kinds of materials. One is called the paramagnets. So the materials, they are classified in three different categories. The paramagnets, so these are aluminum, tungsten and oxygen. They really not become completely magnet. So what happens is the atomic magnetic dipoles, basically the atomic bar magnet, tend to line up with the field, increasing it, but the thermal motion of the particle randomizes this direction, so this alignment does not stay for a longer period of time. So induced magnetic field is of the order of 10 to the power minus 5, whereas the diamagnetic material was gold, copper. So these applied field induces an opposing magnetic field. Okay, so again this is usually very weak. So now then the other one is the ferromagnets, the iron, cobalt, nickel. So somehow they align similar to the paramagnets, but they stay there for a longer period of time. So that is why they create the dipoles and become easily strong magnets. All right. So I stop it here with this. We learned few things about the magnetic field and the magnetic charge and how we find out the direction. So let's stop it here.